ready for us to be on? All right. So I think I'm going to... welcome to the Friday Transportation Seminar. My name is Christopher Monsere. I'm a professor and assistant professor in the Civil and Environmental Engineering. Together with my colleagues John Glebe, Jennifer Dill, and Rob Bertini, we co-organized this transportation seminar. And today I'm also the presenter. So the title of my presentation today is Combining Climate Crash Highway Data for Improved Ranking of Speed and Winter Weather-Related Crash Locations in Oregon. And I should recognize one of my co-authors on the project here, Peter Bosa, is in the room. So this is work we did in the ITS lab over a course of about a year or two, and just finished it up recently in the fall. So I had an opportunity to look at about the 170 so seminars we've given as part of this series, and while my member number isn't 1, it's pretty low. I've given 3 seminars, and I was speaker number 7. So so this was my third event here. So let's go ahead and get underway. So the outline for my presentation today is I'm going to talk a little bit about the motivation for the project, the objectives that we were trying to accomplish, a little bit of detail about the screening methods that we use. So how do we kind of look at the network to identify locations where we might want to make improvements, the data sources that we used, and concentrate a little heavily on the modeling efforts that were conducted as part of this project, and then some results, and show you some of the great maps that Peter made as part of the project. So the motivation for the project. So we sort of intuitively know that speed and crashes are related. And while it's sometimes hard to glean from the crash data the way it's coded, we know that speed reduces the driver's ability to navigate safely, increases their stopping distance, and increases their reaction time. So the map there on the left, while you can't exactly read all of the locations, you get the idea. Those red triangles are all 3 years worth of crashes that had a speed-related component in one of their error causes in them. So the idea for this project is we were looking at speed crashes, or crashes that are speed-related, and we wanted to dig a little bit deeper into some of the other covariates that may be related to speed crashes. And just kind of as an overall summary, about 27% of all crashes, reported crashes that occurred on the state highway system, were speed related, and about 36% of fatal crashes had some sort of speed related component in them. And when we did a sort of an overrepresentation analysis, looking at the different combinations of covariates that were related with speed, one of the ones that popped out as being clearly overrepresented was conditions that happened in either snow or icy conditions. So you can see here about 20% or 17% of speed-related crashes occurred during icy conditions, while only about 6% of those of all crashes occurred during icy conditions. So this was an area that we chose to focus on. And coincidentally, it was also an interest area of the Oregon DOT, who was the research sponsor. They were interested in finding methods to identify locations where they could apply specific countermeasures. And I have an example on the next slide of a couple of those. So they wanted to know where could they put specific countermeasures related to speed and weather-related conditions. And then the second objective was we wanted to look at, well, let's compare these different screening techniques from sort of the more simple to the more complex, and see which, if they identify similar locations or do they identify different locations, and is it worth sort of investing in the more sophisticated methods. And so two examples, and we are focused on crashes that happen during speed and ice, but we could also look at other covariates or other weather conditions. But for speed and ice or speed and ice related crashes, one possible countermeasure could be this automated icing system that the Minnesota DOT has used on a highway in I-35. I think this is I-35 going out of St. Paul, where the bridge has sensors on it, precipitation, temperature, and wind speed. And actually, when the conditions are right for ice formation, the device automatically sprays anti-icing material. So the maintenance vehicles don't need to come to the bridge. The technology de-ices the bridge itself. So, and this is, bridges tend to ice up faster than other sections of roadway because the bottom structure is exposed and it's colder. So, so this could be a technology that could be deployed on bridges or in other locations. We've also got an example. So when you're married to a traffic engineer, when you're going on vacation, your wife still has to take pictures of traffic-related things. So we were going out to Eastern Oregon, and I said, hey, what is that stuff on that they're putting in the pavement? And we snapped a picture of it, and when I got back, I found out that they were putting in a pavement heating system, and I'll show you later on where this location is. But they put inductive wires in the right lane, in the two tire tracks, milled those in and then paved over this. And then in the winter, those generate enough heat that they can keep those two wheel tracks free of bonded ice to the pavement. So so this was an idea. Are there other potential locations for this type of technology? So what were the data sources that we used? We used crash data from 2000 to 2002. We focused on state highways only, and we know the locations of these crashes by their reported milepost. We also gathered a lot of geometric information about the highway, including the number of lanes on the facility, the total roadway width, so including the shoulders, and including any paved medians. We also collected information on the shoulder width and what was the functional class of the roadway, so whether it was an interstate, whether it was a principal arterial or a minor arterial. We gathered exposure, which was average daily traffic volumes. And in the analysis here, we essentially just used 1 year of traffic volumes, the 2001 year, as a measure of exposure on the highway system. And to include some environmental factors, we obtained 30-year average data for two measures that we thought were related to ice formation on highways. One was the mean annual days with measurable snowfall above 1/10 of an inch, and the second was mean annual days when the temperature fell below freezing. So these are data collected by NOAA, and I'll show you on the next slide the spatial resolution of those data. And we were able to associate sort of what was the typical average weather conditions for a particular highway region. No, it's on the next slide after. So in network screening, I guess the yardstick or the measure that you judge whether a technique is effective or not is how effectively does it find locations where correctable crashes are found. So if it finds locations where you can't make a fix, then the technique is not necessarily the best. We want to find find locations that are essentially not typical. So correctable generally is associated with not typical. So we want to find locations that are above average. And so there are a number of ways that you can define average or the performance of a facility based on its the observed crash performance, and those are the measures that we used in the analysis. So what did we use for screening inputs? We used 3 years of crash data, and remember, from now on, everything I show you, I think, except for one figure, is just speed and ice-related crashes. So we've subqueried the data for just crashes that had a speed and ice-related component. We used only the rural highway network. So we had 531-mile sections of interstate freeway. about 2,000 1-mile sections of principal arterials, and about 2,300 miles of minor arterial sections. And again, we use the volume for 2001 as our exposure measure. So we compared, I think, 6 screening methods, and I'm going to briefly describe them here and then show you a little bit more about the others as we go on. So the first method is kind of the most simple method. You could just rank locations by the frequency. So the locations with the highest number of crashes would be ranked, would be sort of your worst location. We skipped using just a simple rate and moved to what we call the critical rate method. And we did it 2 ways. We did it, one, by comparing a critical rate calculated for each functional class. So in this figure, or in this formula, RA is sort of the average rate. So the average rate for an rural interstate facility or a rural primary arterial facility. And you can calculate, based on M is the exposure measure, you can calculate a critical rate. And any section that exceeds that rate, you can say is essentially enough above average that should be warranted as ranking. And so we did it by functional class, and we did it by what we called climate zones. And I'll show you on the next slide how we incorporated the weather into this. So you can, the general hypothesis that we were working on is that you can better define average by the more finely you aggregate different facility types. So, and I'll highlight that in a couple figures later. This is the method that I had mentioned before, this potential for crash reduction. You estimate the average crash performance based on a multivariate regression model and combine it with an empirical Bayes technique. And this is the more sophisticated data-intensive model or method. So on some slides it's abbreviated PCR, but that's the potential for crash reduction. And essentially we're going to estimate the average number of crashes, and we're going to try and estimate that as precisely as we can based on the different facility characteristics. And the observed number of crashes, however higher above the average that is, that's the amount that we're going to say that's the potential for reduction. So it's this much in terms of count above average. And I have some figures later on for that. And then I don't think there's anybody from my safety analysis class in here. So some of this, they've seen some of these slides. But when we have just the frequency, and we look at frequency counts over time, they're generally, there's going to be a lot of variation in them, and will not give you sort of the best picture. But if you adjust them with these same models developed for the potential for crash reduction, you can get a better estimate of the expected frequency. So we ranked it by that last, that's a 5th method there. So so now we get into a little bit more graphical information here. So here's the state with the mean annual days with temperature below 32 degrees Fahrenheit. So those are and the darker shades obviously had more days with freezing weather, or freezing days. And if we sort of overlay the mean annual days with snow accumulation greater than 1/10 of an inch, you can clearly see the Cascade Range and the Blue Mountains and the Wallowa Mountains in eastern Oregon. Again, here the darker colors indicates more days with measurable snowfall. And I think Peter spent some time playing with the transparency of these 2 layers and sort of overlaid them and divided the state up into 9 different climate zones. And so, and with pretty distinct weather patterns in terms of freezing and snow patterns. So we have and Oregon is one of the states where you can do this. Where I went to graduate school in Iowa, I think there would be 1 climate zone. So we have this unique that makes it a little bit more interesting. We have 1, the coast and the Oregon coast, 2 2 is what we call the valley and foothills. And then you see 3 and 4, sort of the Coast Range mountains with a little bit more sort of colder and snowier days. And then clearly the Cascades, the Central Desert, and then the Northeast. So 5 and 9 are the areas where we have sort of the most winter weather-like conditions. So, and why did we want to do that? Well, so here shows the average crash rate for each of those, for speed and ice conditions. For the red bars are interstate facilities, the blue bars are principal arterials, and the green bars are minor arterials and collectors. And so when we just look at it by statewide, you can see that compared to some of the locations, the Cascade and the Northeast, where we have a lot of winter weather-related conditions, the locations where we don't drag down sort of the statewide average for speed and ice-related conditions. So if we were comparing using, in the first method, just the zone or just the functional class rate, if we compare, say, a rate in a location where we expect more snow, it's going to look above average compared to the statewide. But if we compare it in its zone, it's not going to look so unusual. So the idea here is that by dividing it up into the weather zones, we're better able to just say what's typical, what's average in each of these regions. And so you can see the Coast Valley, the South Coast, the Columbia Basin in terms of the crash rate. So that's the number of crashes divided by the travel in that area, is much lower. But the 3 areas where we had a lot of winter weather also experience a higher rate of speed and ice-related crashes. There's no interstate on the coast, and there's no interstate in the central or in the North Coast mountains. And this little piece of the freeway here in the Northeast just barely cuts across the. So this is in section 7, the Southeast. This lip here just barely cuts through here. I-84 cutting through here in this area 7. So rates can sometimes give you a different, rates and frequency can sometimes give you different pictures. And so here's just looking at, on these plots, on all 9 of these plots, these are each of the weather regions. And this is the traffic volume across the x-axis and the total number of crashes across the on the y-axis. So you can. And this is the one figure that I have total crashes, just to show you the difference between the speed and ice crashes. So you can clearly see that most, we have sections that have total over the 3-year of 200, a little over 200 crashes in the valley and foothills. But in the other regions, we definitely have much lower crash observations. And we also we don't have nearly as much volume as we do in the valley and foothills. When we look at the speed and ice crashes, though, the picture looks a little bit different. Notice how in this slide we sort of had these, and you can't really see the pattern because they're all on the same scale, but we sort of have this increasing trend as more, and this is typical, as you have more volume, you expect more crashes. But in this speed and ice-related plot, again using the 9 climate zones, we can see a couple things from this graph. Again, ADT on the x-axis, number of speed and ice crashes on the y-axis. So now the frequency of speed and ice crashes obviously is higher than in those the 3 zones where we observed more winter weather conditions. And the shape of this is a little bit different in that there's a lot of speed and ice crashes, and there's not as much volume in these 3 areas. So the higher volume sections are generally in the valley and foothills area, and that's in an area where we don't have a lot of winter weather. So they have So they have lower. So the trend isn't that sort of increasing with volume as apparent as it is in the total crash picture. And then just looking at snow days, again, so this is snow days on the x-axis and total speed and ice crashes on the y-axis. So you can see that the Cascade Mountains, 85 to 90 days with snow kind of runs the gamut over the number of observed speed and ice crashes. But in the other zones, we don't have nearly as many days with weather-related conditions. So these plots are just sort of exploratory, sort of confirming what we might suspect, but it's a very easy way to look at the data to start making sense of it. And so we're going to go the next step then is we're going to develop some multivariate regression models on the assembled data, and these are often called safety performance functions. We use the negative binomial regression formulation. We use the software package R, which is open source software package. There's the website if you want to investigate it. And we selected basically the best fit model for each of the three functional classes to better predict average. And so I'm going to walk you through some of the modeling and the results. So after assembling and sort of triaging a number of data, we sort of settled on these as variables to include in the model. We modeled the total speed and ice crashes for each 1 mile section for year 2001. We used the measure of exposure, the ADT, the snow days, the total surface width, so the total width of the roadway including shoulders. Then we sort of made a proxy measure of sort of available roadway width. So we took the total width divided by the total number of lanes. So we had the total width of roadway divided by the lanes. And this would be sort of a measure of how much sort of cushion you have. So if you had 11-foot lanes and 2-foot shoulders, and you had 2 lanes, vehicles are a little bit more compacted there or closer together. But if we had wider lanes and more shoulders, vehicles had a little bit more room to maneuver. So rather than including just the number of lanes, we included this width per lane. And then we also added in the posted speed limit code. We wanted to include some information about geometry because we sort of found from our analysis that horizontal curvature and ice-related crashes had a lot of were related strongly as well, but we weren't able to sort of assemble a measure of horizontal curvature that we were able to include in the model. So we were looking at 1 mile sections, and we tried a number of different ways to include that measure, and none of them seemed to quite be satisfactory. So this is a rather busy plot, but I'm just going to point out some patterns. So these are all, down here in the corner we have the total speed and ice crashes. So I'll explain this plot a little bit. So this is the dependent variable that we're modeling, total speed and ice crashes. These are the potential variables that we could include in the model. And the way you read this scatterplot matrix is that so it has the axis on all 4 sides. So here it's speed and ice crashes in 2001 from 0 to 8. And then here's the average, the traffic volume from 0 to about 40,000, I think. And then here's snow days from 0 to 80 and 0 to 80 and 0 to 80. So you can see the relationship between all of the variables very easily. The plot is actually symmetric along this axis here. So this is just, you'd get the same information if you look on either side. So you've seen this trend here, this plot of the speed and ice crashes versus volume. It has this kind of sort of triangular shape, which is a little bit different than sort of the total plot. you see two variables that are clearly correlated, the width per lane and the total surface width. And since the width per lane is the surface width divided by the number of lanes they are, so we were only going to include either one or the other of these variables in the model. You see some other patterns in the data. So here we've got the surface width and the volume range, and you see the surface width, the total surface width is pretty well distributed across all different volume classes. And then here you see the speed code, and you see this line far to the right here is all 55 miles an hour. So you see that there's a lot of sections that have 55 mile an hour. And I should have mentioned that this scatter plot is only for principal arterial. So the advantage of making these plots is it helps you find some outliers. So this point here where there's a 65 mile an hour point on a rural principal arterial is sort of a result of where it's not quite a freeway, but it's not quite an arterial. So we had we're able to do some data checking by looking at these different plots. So these are useful in terms of gathering the different patterns of the data. All right, so we developed 6 alternative models for each of the 3 functional classes. We incorporated, so you can see the models there, including snow days and width per lane, or width per lane and surface width. Ran those through the negative binomial regression, and I'm only showing you for the 2 interstate and principal arterials. But we measure the significance of each variable, sort of a pseudo R-squared value for the model, Akaki's information criteria, and then another parameter called the overdispersion of the data. So output of the negative binomial regression. And we selected sort of the model that we had sort of the best, that we thought was sort of the best fit for interstates, for principal arterials, and for minor arterials. And here's a 2-dimensional plot of those models. So even though it would be more than 2 dimensions, we're modeling total speed in ice crashes based on the exposure, snow days, surface width, and speed code. The purple area is the modeled number of crashes, and the black open circles are the observed number of crashes. So the model incorporating those measures seems to fit the data pattern fairly well. The principal arterial looks a little bit as well. The one that there's not a lot of minor arterials have such low volumes and such low crash counts that this model doesn't fit as well. You can see there's many sections that have no observed crashes on them. So this model only has the number of snow days and the volume exposure. So then we took those models and we were going to combine them to make a better estimate of what the expected number of crashes were on each facility. And we do this with a technique called empirical Bayes methods, pioneered by Ezra Howers, an emeritus professor at University of Toronto, and used by many people since in the evaluation of safety performance. And so the idea here is you have a safety performance function that predicts the expected number of crashes against the multivariates. Here it's just showing volume. But we also observe some number of crashes for a section with some volume. The pink dot then is the modeled volume. And we use these 2 clues. We combine them together with the overdispersion parameter out of the model to get to what's called sort of the best estimate of the expected number of crashes. So in one sense, the model gives you average, but there are some things that are uncaptured in the model, and the observed number of crashes at a location also gives you some clue. So you combine those 2 together to get a best estimate of the expected number of crashes. And then we can use the best estimate of the expected number of crashes, and we plot that. Here this is shown plotted against the observed number of crashes for each section. And you can see at this one point here, if everything fell along this 45-degree red line, then we would observe the same number that we expect. But in this location, we only expect about 3 crashes, but we actually observe like 15. So this excess is the potential for crash reduction. So the thought is that there's about 11 crashes that are above average. So there's some potential there. There's something unusual about that site, that there are 11 more crashes there than what we would have expected. And we've tried to make the estimate as best as we can. We've tried to incorporate the weather information, the geometry, and so we've tried to define averages as best we can. And so this section, the higher it is above average, the more it should warrant an investigation. So how do the methods compare? So this is just a matrix here of the 5 methods and how they ranked. And how they identified the top 20 sites. So did they identify the top 20 sites? How many of those did they identify in common? And so the frequency method, and then the frequency method, we adjusted it with the empirical Bayes approach, had the most in common, and you'd sort of expect that. They had 16 sites identified out of 20 as common sites. The critical rate with the functional class and the one with climate zone compared well with each other, about 9 sites, and then also with the frequency method. But the potential for crash reduction, which is generally considered sort of the most sophisticated and the best method, didn't compare all that well with the other methods. And I had kind of some hope that it would compare fairly well with the critical rate with functional class and climate zones, doing a pretty good job of sort of trying to aggregate and define the average crash rate for a facility. But it didn't do as well as I had hoped. So not that I was biased, but I was just kind of the thought that I had that they might line up. So let's walk through some different maps of the locations that were identified. Maybe it'll highlight some of the advantages of each of the methods. So just looking at the total, just ranking things by frequency, you get what you probably might expect. You get a lot. I've shown the top 20 locations. So you get locations on I-84 in the eastern Oregon, and then you get locations around Mount Hood, and then a couple of locations on Oregon 58 over Willamette Pass, and then one location on Santiam Pass. Now the purple, or the fuchsia, pink, that shows with the empirical Bayes adjusted, and those, as we had shown, those were fairly in common with the frequency method. And looking at just comparing it, ranking them by just their functional class rate. So how far above were they above the rate for their entire facility? So, and then comparing that with the frequency method, you see that it sort of moved off these locations where you observed sort of on the edge here, and sort of focused more on kind of the locations that observed more crashes. You still have the Mount Hood, and when we use the rate method, these facilities here that were identified by frequency didn't appear in the rate method. So here's the method. The zonal rate was the one that I thought might compare the best with the potential for crash reduction. And you'll notice here that sort of the locations that had observed were ranked high by frequency. They were more in line sort of what's expected based on the weather in that area. And so they didn't get ranked by the zonal rate method. But some locations, so some locations on the entering into the weather area ranked higher. So these might be areas where a driver is not maybe not be expecting weather conditions, and this is kind of the first weather area that they hit. And interestingly, down here, this method did pick up this one location, the Siskiyous, and none of the other methods identified this location. And I'll skip through this one. So here's the two that I thought I mean, theoretically, and sort of they appeal to me sort of as being the best. And they did identify a lot of sites in common, although the potential for crash reduction method identified about 5 sites that identified. Those are the 5 sites that identified in common. And interestingly, it identified the number 1 site and the number 2 site and the number 3 site and the number 5 site by both methods were found. So they did have, even though there was, they didn't compare well in numbers, they did identify the top locations they compared well there. So let's, and these were some of the nice maps I was talking about that Peter helped create. So let's look at those 2 sites. And this is the one that was identified, 1 by the zonal rank method and 2 by the potential for crash reduction method. And it's down here on Oregon 58 coming out of Eugene going over the Willamette Pass. The red dots are the speed and ice crashes over the 3-year speed and ice crashes. And interestingly, on this section, you don't see any other speed and ice crashes except sort of right here, sort of perhaps downwind of this. I forgot to look up the name of this lake. Does anybody recognize it from? I can't remember what it. But
Dexter Reservoir?
Is it Dexter Reservoir? Okay. So these locations are here, and you can see a nice kind of a wall here. So perhaps there's some shading issues that allow this highway gets icy before other locations. So this may be a section that even though there isn't necessarily a lot of speed and ice related crashes, that it may be someplace that may require some priority maintenance. And then looking up on Mount Hood, there was a number of sections that were ranked fairly high up on the Mount Hood on Oregon 35 or 26. But this one section here where there's a lot of curvature just past I think this is the White River here. So on your way to Meadows. So this was a section that was identified by both methods. So up here in the Cascades, countermeasures are a little bit more challenging on what you would. I mean, they get a lot of snow, and people expect snow up here. So this location, a potential solution isn't maybe as apparent as the previous identification. So here's a final map showing all of the methods and all of the different locations they ranked. And I'm not going to go over the other locations, but the potential for crash reduction also identified some other outliers out here on 22 and 18, an area over here by Bend that were identified as being more unusual than other locations. So, but a lot of the other methods picked up sort of the same area. The blue arrow there is where they put in the pavement heating section on Ladd Canyon. So there's a section there where trucks, you have to chain up, and then they get to unchain, and then there's a small section where they need to rechain, and they're not very motivated to rechain in that section, and so there's been a lot of trucks that have overturned or jackknifed in that area and end up blocking the highway. So that was their motivation for putting that pavement heating section in. To keep the lane free so the trucks don't jackknife and block the highway. So I haven't seen a report on how effective that's been. It's operated last year, and it did keep the pavement, the wheel tracks bare, I think, for almost all but one storm event for that year. So my conclusions are that the methods identify different sites. The potential for crash reduction seems to be the most unique. It's hard to say which method is superior because you would need to sort of go through each one and see which method sort of identifies sort of the most, after you do your site investigation, which method allowed you to find the most correctable crashes. That's the yardstick we're using. But many other researchers have sort of suggested that the more sophisticated methods, including the potential for crash reduction, are better. And these results lead to that, also sort of suggest that as well. The models that we developed, the safety performance function models, could be improved. We could use, obviously, we could use more than 1 year of data. We could use better, we could have more exposure method. We could, and I since found some more, sort of more, instead of 30-year average, more annual, so annual measures of weather, which would be a finer detail. And perhaps using some of ODOT's road weather information system, you could even associate the weather condition with the crash with the actual weather condition that was measured. So the modeling effort on the weather side could be improved. You could apply this method to other weather-related events. So we could look at crashes during based on the amount of rainfall, or based on precipitation. We might also want to improve our method with what's called a sliding window approach. So instead of just looking at fixed 1 mile sections, we may want to look at a 1 mile section, step it some distance, and then look at that section, so that we don't have a place where we have, so say we have a location that may be fairly high, but since it's split between 2 1 mile sections, it misses our ranking method. So if we did a technique where we slid the window along, we'd make sure we didn't miss any of those locations. But Peter needed to graduate, so. So I acknowledge my co-authors and co-collaborators, Robert Tini, Peter Bosa, Casey Nolan, Tarek Al-Sayed, and Delia Chi, and then acknowledging the ODOT Technical Advisory Committee that sponsored and contributed to, and helped us with the research. So with that, it's time for questions. Oh yeah, and remember to use the microphone. So in front of you, hold the touch the touch button and then hold it down while the red light's on, so that our web viewers can hear your question. So Ines?
I just want to figure out something about the pavement heating system and the icing stuff. I thought that when the ice starts to melt or something, that would cause more slippery roads or increase more crashes or something like that.
So in winter weather maintenance, the challenge is not allowing the ice to bond to the pavement. So by keeping the pavement warm, it doesn't allow the compacted snow to bond to the pavement, and there's enough heat there that the trucks can kind of smash up the ice, and then it's above freezing, so that the water doesn't refreeze. Did I answer your question? Okay. Charles?
Just had a question. Just had more of a question about countermeasures. It seems like there should be more options than just either heating the pavement or putting some kind of spray. Is there a way to, I don't know, provide information to the driver to say, hey, we're serious about this. This is a dangerous road section. Slow down. I mean,
yeah, and actually that was the motivation that started the DOT sort of encouraging us to look for speed and ice related. They have pavement temperature and ice detection sensors, and then they can link that with a variable message sign. They're actually considering one on Highway 140. It may already be installed on the Lake of the Woods Highway out of between Medford and Klamath Falls. Unfortunately, that didn't show up on our ranking method as a potential place for a countermeasure, but there are technologies like that, information, so communicating to the driver, as well as communicating to perhaps to maintenance activities onto where locations. Of course, it's their road. They sort of know where the problems are, but sort of giving them an idea that hey, this location seems to be worse compared to others. Could you give it some preferential treatment? Maybe another potential countermeasure.
I don't know if you had a chance to speak with ODOT after you gave them this information, but were there, just from their personal views, were there any places that they were really surprised about that maybe they hadn't considered doing some sort of mitigation or anything like that?
No, I hadn't a chance to get that kind of feedback from the sort of the maintenance side of things. So,
We have a web
All
question.
right.
Asking if you could include lighting conditions, or if you think that was a factor, could be a factor in any of these road segments, and whether or not you could even get data to include that in a model, if you think that could improve it.
Yeah, so I have another research project that is looking at some illumination, and including illumination in some of the analysis. So certainly you could get the presence or the amount of illumination, and you could include that probably with sort of maybe more appropriate, not with winter weather, but more maybe if you were looking at precipitation events, and maybe horizontal curvature with the presence of clouds and making things a lot more dark in the winter weather, or in the weather conditions. So it may be something you could incorporate. Use the microphone.
The ice-related crash may induced by the slope and the curves, the geography.
Yeah.
Yeah. So how? What's the criterion for you to choose the data? They say the data is ice-related, but the crash may not induced by the ice, may more impacted by the slope.
Yeah.
The curve.
Sure. Yeah. So. Yeah, so I mean, there could be other causation measures for the crash, besides the ice. I'm not saying that the ice and the speed caused the crash. I'm saying that they were contributing. They were identified factors in the presence of the crash. It's very hard to sort of glean causation from the crash data. In fact, there's even the idea that they checked the crash is speed related while there's icy conditions. There's a lot of bias in that piece, in that if a crash happens during icy, the officer or the citizen may report, well, you were obviously traveling too fast for the conditions. So you get the definition of speed related in the crash data is less than perfect. So it's not a measure of like how fast they were going. It's sort of just a judgment whether the speed was involved. So, yeah, Peter.
I forgot how much work we put into this. Now I remember why I was in such a hurry to graduate. But, I was curious. I know you've mentioned that you haven't had feedback yet from some of the ODOT maintenance people, but given that the potential crash reduction method and both the zone rate method identified 4 out of 5 of the top 5 sites identical, has there been any interest by ODOT and perhaps doing a more thorough investigation of those particular sites, maybe perhaps site visits to gather this kind of geometric data?
Yeah, no, we haven't taken the road show down there yet. So, but that's obviously a next step in a sort of our information dissemination. So.
With your initial scatter plots where you were examining your data and you had those outliers like with the speed limits, did you include those outliers in your model?
Yeah, those are. We went back and sort of verified that they should be included. That we found a few sections that had been misclassified. That had a few sections where the ADT didn't make sense with its classification. So we kind of used those plotting techniques to find misclassifications in the data and then eliminate any outliers. So.
Another web question.
All right.
You mentioned the heated pavement and then also the spraying of de-icer, automatic de-icing. What are some other methods to address some of these problem areas?
So I think we mentioned sort of the traveler information systems and sort of the advanced maintenance strategies would be the two other sort of relating to speed and weather conditions, two other countermeasures you could use. So if you knew a location was potentially that there was a lot of speed and ice crashes before a weather storm came, with sort of the right forecast, you could go out and sort of maybe do some anti-icing or pre-wetting like they try and do in the city of Portland if they get the forecast right. Not the city guys, but the weather guys. Okay, so I have to check who the. So next week we have Susan Handy from UC Davis giving a presentation on bicycling in Davis, a critical look at the first platinum bicycle city in the U.S. So look forward to it.
I anticipate a large crowd.
Yeah, because we're trying to be the second city, right? So.
On a blog, so.
All right. Well, thanks for your attention.